welcome everyone. Good morning, afternoon, evening, depending on where you're joining us from. Thank you everyone for joining us at the SCG Near Surface Geophysics Technical Section Student Subcommittee's webinar on SimPEG, which is part of our webinar series on open source software. My name is Chris Terra. I'm one of the student subcommittee members, and I'll be your moderator for today. Today's presenters are Joseph Capriati, Lindsay Hagee, and then Sagi Kang, who will be joining us shortly. Before we begin, so the model for this webinar will be a short presentation, and we followed by some extended Q&A sessions. At any point, if you have any questions, feel free to drop them into the Q&A window at the top. Let's see here. Yeah, cool. Depending on where the presenters are in their presentation, they'll either take a bit of time to quickly answer any questions if it's a quick answer, or they might take a break at a good point to run through a few. Afterwards, there'll be some time to go through some more questions in some more detail, depending on how timing is looking. Let's see here. I think that's pretty much it. If you have any dedicated questions towards the end of this, feel free to use the raise hand function, and then we'll allow you to be unmuted so you can verbally ask your question if you wish to do that. This webinar is being recorded and will be uploaded onto the SCG YouTube channel in our open source software playlist, so keep an eye out for that if you just want to come back and review any important bits of information. So with that, I will hand it off to our presenters.
Awesome. Thanks, Chris. I'll steal the screen share first. All right. Are you able to see that?
Yes.
Okay, awesome. Thank you. Well, thanks everyone for taking the time to join us today. Really pleased to be connecting with the SCG Near Surface community and be a part of this series. Pleased to be here today with Joe Caprioti, who's a research associate at Colorado School of Mines, and Sagi Kang will be joining us soon. He's a research associate at Stanford University in geophysics. And I'm Lindsay Hagee. I'm an assistant professor at UBC. And we're all involved and contribute to the development of SimPEG. And the work that we'll be showing today really builds upon a lot of the work by the broader SimPEG community. So we're the three folks who have the pleasure of being here today, but we rely on and have benefited a lot, of course, from the rest of the community. I'll share these slides afterwards. We're going to have some links throughout. So the link to the GitHub repository, if you want to follow along, is right here. So just some context first on the types of problems we're interested in solving is we're looking at inverse problems. And so the general setup is we've got some data that have been measured over the Earth. In this case, we're going to be looking at electromagnetic data. We'll hopefully have some assessment or understanding of the uncertainties on those data, the noise levels, and the ability to forward simulate those data. So that is capabilities that SimPEG is going to provide. And then the goal of the inverse problem is that we want to take those data and try and find an Earth model that's consistent with those data and any other assumptions and knowledge you might have about the subsurface. And so this is where SimPEG comes in. So SimPEG, the naming sort of stands for Simulation and Parameter Estimation in Geophysics. It's a common framework for simulations and inversions. And there's a few perhaps of the motivating factors here of why we started SimPEG and why we continue working on SimPEG is being able to accelerate research, build upon the work of others, and have some fun working actually with a community of people. And so the SimPEG website is simpeg.xyz, and you can see a bit about the methods that we have plugged in there. So where SimPEG is at, there's a lot of aspects that we'd call, in a sense, kind of production ready. By that, we mean that it's pretty efficient, pretty stable. There's lots of good documentation at this point. So things like octree meshes, being able to simulate equations in 3D. Then the methods talking about gravity, magnetics, DC resistivity, induced polarization, and EM1D is going to be our focus today. There's other areas that we do have code that is working, but we say it's in a bit more of a research stage, meaning we have some more work to do on efficiency and documentation and such. And that would be 3D EM as well as joint inversions. So if those are things that you're interested in doing some research on, we have some tools for that, but you'll want to get connected with the community to get up and running with those. So coming back, what does SimPEG actually solve? So we're going to formulate the inverse problem as a optimization problem, where what we're going to try and do is minimize a data misfit term and a model norm term with a trade-off parameter in between the two. And there's lots that you can do to play around with, especially this model norm. We can think about, an L2 norm to get a smooth model. We can think about, sparse and compact norms. So we'll touch on a few of those types of things today. So we're going to go through really the dive into the code today. If you're looking for some more information kind of on the background theory of inversion, we gave a couple MTNet, these M&R talks a while ago. Doug Oldenburg gave one on the fundamentals of inversion, and I sort of jumped off that and talked about how we take these pieces of an inversion workflow and implement them in SimPEG. So if you want some more information, those are some talks that we can point you to. So for today, the data set that we're going to be working with is some airborne EM data collected over the Monterey Coast in California. And so Sagi Kang kindly set us up with these data, and these are data that he knows well and has been working with quite heavily in his research at Stanford. And so, as many folks know, the Central Valley is, a really important region for agriculture, producing food, both for the U.S. as well as for Canada. A lot of our produce is imported from California. And so the groundwater situation there is quite concerning. And so airborne EM is a really valuable tool for trying to understand groundwater and also to manage aquifers. So the data set that we'll be working with is their SkyTem data that were acquired in 2017. There's some monitor wells. There's 800 line kilometers of data, and it's talked about more in this publication here. And so these are publicly available data that we'll be working with. And we're just going to pick a single sounding, but you'll get a chance to see if you want to play around with some others. So the goals for today, we'll introduce the SimPEG framework, talk about how to use that for forward simulations and inversions, and then go ahead and invert a sounding from this data set. So a couple things, I'll just share these links with you briefly, and as I mentioned, I'll drop the slides in the chat so that you have them. If you want to get connected with SimPEG, you can install it this way. There's links to the documentation. We send out a newsletter about monthly, and there's also a Slack group where you can get connected and ask some questions. There's some additional links. This is really just meant to be a useful reference page where we've got, some user tutorials that we've been working on developing. These are quite comprehensive. We've also got some open source educational resources through this geosci.xyz website that might be of use to you. And so with that, I want to say thanks everyone for being here today. And I'm going to stop my screen share and turn the floor over to Joe.
Thanks, Lindsay. So yeah, I'm going to go in, and you guys all should have seen some links in the announcements to some GitHub pages. Hopefully some of you guys got started up. I know we were contacted by a couple people to make sure that it was working for them, and the environment was growing. But what we're going to do is basically work through this example together and show you kind of maybe the way I would do it. It's not the way that everybody would do it, but hopefully I'll be able to tell you all of my thinking and explain some of the choices that we make, and you guys will learn about SimPEG and the structure and how we set things up. So my goal is to be able to show you guys how we represent a airborne EM survey, specifically the SkyTem system, using SimPEG objects, like using SimPEG, because we need to be able to represent that system to be able to model it. So then we'll work through how we can model it, how we can do some simple forward simulations, and then work through the inversion process, starting with at a very simple level and then getting to more advanced levels as we go on. Yep, and there, thank you for sharing that on the page. Yep, there's the GitHub link. Awesome. I'm gonna share my screen and we'll start from there. Basically exactly from that link. Okay. So you guys should be able to see I'm up on this GitHub page right now, right? That's where we're going to. So there's a few examples about how to get it set up. You could use either Jupyter Notebooks or Google Colab. There's a slightly different, slightly few changes that you'll need to do, but what we're going to be working through is this live SkyTime system, this live SkyTime notebook. So let me go through here. So hopefully you guys have either done this, installed Python locally, or gotten an environment set up. So I'm going to skip a few of these steps here because they're all set up. So let's get into this thing. So I already have all my repositories utility code. So if you're familiar with Git, you likely already pulled this data ahead of time. You've likely already pulled this. If not, you can get a collab up and going. I will show you how to do that very quickly as well. So if I want to open a live notebook up in Colab, and go to Colab. Already got it kind of open here and start up a new notebook, but we're actually going to open the notebook. So what's nice in Colab is that you can directly copy notebooks from GitHub pages. So I have this repository link and paste it here. Colab sees it and it sees the notebooks that are there, right? So if you wanted to, you could start right from here. You would get this notebook up and going, and then there's a few steps that you would need to do to get it to work properly. So it's detailed down here as well. So you would need to install SimPEG at the top of it. So what we would do is create a new cell above this one. There we go. So you do this, it would start to, you'll see some information about it downloading SimPEG and discretize and installing this stuff into the environment. You'd also have to copy a few small little pieces of utility code. So what this is there is a configuration file and a small little parser that we've written to kind of go through it. So that's just going to get those through files, and then you'd be ready to go. You can work through this live notebook almost as is. There's a few notes about what you'd have to change if you're on GitHub, but it should work from this point on. Alternatively, so I'm going to work with this in a Jupyter notebook very quickly. I have my terminal. I'm going to go to where I've downloaded, where I've copied all of this code. This is your surface tutorial. Get my Jupyter, activate my Conda environment. So I've already installed the environment file, everything going. Now I'm in this Conda environment, which you can tell from the prefix on the terminal command, and open up Jupyter Lab. So this should start up the Jupyter Lab. It'll open up in this window here, and yes, it does. Okay, so I'm going to work through it on this page, but you guys should be able to follow along with this in Google Colab as well, just using the simple steps that I kind of showed you there. Okay, those it's not best practice, but I think it'll work well for this. I'm only going to import things when I need them for this, so I can show you exactly where they come from, and I can talk about it when that happens. So right now we've just got a few things. Importing standard pandas to parse some data files that we have. And then I am importing some SimPEG. So with SimPEG, what we're going to be working with is the time domain module of SimPEG. I'm basically just importing that. A lot of the things we need will come from there, so I'm just importing that. And then discretize is our package that generates meshes, which we'll need later on. Now you might get some warnings here from pandas. Basically, it's saying that, you know, when pandas the next version of pandas is going to require something else. but it's a warning, so it'll be okay. So now let's think about reading in this data set. In general, the SkyTEM systems have, as they collect data, they have this two sorts of classes of their data. They have a portions that come from a low moment, meaning like the transmitter has a lower current, it has a higher ramp off time, or higher turn off time, to be able to get to more sensitive information to the near surface, and a higher moment source term that has a stronger current, a larger source moment, so we can hopefully see deeper. And then this hexagonal loop transmitter, and it has a dB/dt sensor on it. So it's measuring the time derivative of the magnetic flux density. I'm gonna try to be consistent with that term because I tell my students all the time that I may say magnetic field when I actually mean magnetic flux density, but if I write a B, it's always a B. Okay, anyway, so in the data set, there's two things that usually come with a SkyTEM data set. There's a configuration file that just tells us all those parameters about the setup of the survey, essentially, and a data file. So the data file contains all of the recorded data. There's been, let me get started with this configuration file. So I'll show you guys what this looks like. So this is a very common file that is that's provided with a SkyTEM-like survey. So there's things like a name for the file, the positions of the receiver coils, some information about the gates, the coordinates of the loop, the transmitter loop. So there's 8 of them, the number of turns, the waveforms of each of the points. So this would be like the low moment, the high moment data set. And if this is, I thought I'd increase my font, but I'll make this a little bit bigger. Essentially, there's all the information that's in here that we will need to set up a survey. So the time gates, so it's a time domain system. So it has a current going through a loop that gets turned off, and that causes currents to be induced in the subsurface. So we have all these time gates here, looking through it. So essentially what I've already written for you guys is this sort of parser for this file that's going to get all of this information and just make it accessible to us in SimPEG. It's not super interesting, but it's there if you guys want to look through it. So for me, this file is located in parse my text file. In this data folder relative to this, it's this file. If you're on Google Colab, it should have downloaded it directly to the same directory that you're in. So you don't need to have all those relative information. But for me, and if you're working from the GitHub, it'll be here. I'll show you what this parser did is essentially put all of the information from that file into a dictionary. So we can essentially query the file for the things we need. This is a dictionary. There's some general information, waveforms. It's all just in arrays ready for us to use. We just have to query it for the things that we need. Now the data file is just it's been parsed already. So this data file has done a few things. It's been processed already. And what I mean by that is that it's not specifically the raw data that came from SkyTEM. Processing this data on its own is a bit beyond the scope of this and on the focus of this thing. But if you're really interested, we can probably point you to some good resources and some good examples about how it is processed. But in general, the data is collected along flight lines and then sort of windowed into stations and separated into low moment and high moment data sets. There's some information about the file. So we've already parsed it for you and gotten into a decently easy to read format. But we're essentially just going to use pandas to open it and read it. If you're in Colab, you actually didn't have to download this file. Pandas is smart enough to read this right from the internet. I can do this, right? It pulled it right from GitHub for me. I didn't have to do anything. So you'll see in this file, it was just a simple CSV file. There's line numbers, records, which are basically the station's GPS coordinates, some elevations, the altitude of the instrument, and all of this data. So there's low moment data. It's all hidden in here, but there's many, many columns. So low moment data, many channels, high moment data, many channels, and each of those things has a standard deviation associated with them. These sort of standard deviations came from that sort of statistical process from windowing the data along a line. So it's averaging it along the line to create a station. And there's some sort of statistics associated with that average that have gone into this standard deviation. We will use these, but we'll get to the end. We'll estimate standard deviations as well to see if these were a decent representation of what we see from the inversions. Okay. So in the meantime, we've got all of this data here. So inside this data, the first thing that will tell you is that there's missing data points. So all of there's not a data point for every low moment time gate at every station or every high moment time gate at every station. So in that data file, it's represented as 9999. So the first thing I want to do is just replace all of those with nans. And that's going to make it a little bit easier for me to plot things later on. Instead of just ignoring things at 99, this will make it so I can automatically ignore those files or ignore those lines when I'm plotting things. Okay. So with the pandas data set, so this is read into pandas, I can simply access any of these columns by their names. So we've got our UTM-X and UTM-Y. So let's just plot up all of the UTM and see what our survey looks like, right? So this should look pretty familiar to what Lindsay was showing on the opening slide, right? We've got several lines, we've got some cross lines, some missing data points internally inside this survey, but this is all the data places that we have stations at. To get started right away, though, there's a few bits of information that we need from that GEX file. I can parse it and get the number of, I need to know how many gates, how many time channels we're expecting for each of the low moment and high moment data sets. So inside that GEX file, the low moment data is associated with channel 1. And then inside that, there's a no gates, the number of gates. So this is inside that GEX file, right? It's coming up here, it's looking at channel 1, and it's getting the number of gates. So there's 26 potential gates for the low moment data sets. Also, the GEX file tells us that we are going to skip a few, right? So there's a remove. It's not technically. Again. What's going on? There we go. Okay. The issue is I'm sorry, my keyboard is not giving me a square bracket for some reason. So we have a remove initial gates, right? So this is going to tell us that we have 21 gates associated with the low moment data set. Correspondingly, all the high moment, the information in the high moment, is all going to be in channel 2. Right, so now I've got there are 21 potential low moment gates and 28 potential high moment gates. That is the maximum amount of gates that we'll see at any station. So this data file will have the number of low moment gates of actual recorded data, the same number of standard deviation or relative error estimates. So those standard deviations in that file are actually relative errors, so they're percent standard deviations. So we're going to have to take care of that, and we can do that later on. You'll see how we take care of that in inversion. So it has low moment gates, data, error estimates, and then high moment gates, data and error estimates. So all of the data is in here. You guys could go and choose whatever line you wanted, whatever station you wanted, and work through this whole thing. But what I'm going to do is let's go in and look at a line. So let's say 26301. With pandas, I can easily tell it to group everything by the line number. So this will return an object here that sort of I can iterate through very easily by line number. I can find this it'll give me back everything with a specific line number. So let's get one of those lines. So line grouping, I'm going to get a group. I'm going to get that one that's associated with the line number I just said. Let's look at that line. So this is another pandas data frame, and it has all of the records associated with that line number that we gave. 139 rows. Let's look at the data along this line. Remember when I said that there's the number of low moment gates, and there's a bunch of standard deviations, and the number of high moment gates. So before that, in this file, if we're thinking of this as one big array of things, right? There's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 columns before we get to our data set, before we get to any of the columns with the data. That's where this 9 comes in. So I'm looking at accessing by columns, and then I'm going to go from the 9th column to the 9th plus the number of low moment gates. The second for the high moment data, I'm just skipping those same 9, and again, I'm going to skip all of the data set that's associated with the low moment, so the data and the standard deviations, and then I'm going to grab all of the high moment data. So I'm just grabbing those data sets from that line. So right, this is the low moment data, for example. So this is all of the low moment data associated with that one line. Okay, let's see what it looks like. Often we can plot these things. We plot these dBdt data sets on a log scale. So I'm going to do a semi-log Y plot that's going to automatically give me a log scale on the Y-axis. Let's plot it as against the Y coordinate of the data. So this is all the low moment data. Actually, I'll do that so that doesn't pop up. You can always add a colon at the end of a line in Jupyter Notebooks to hide the printed output from that. So this is all the low moment data. And remember what I said when not all of the low moment data is available at every station. You can kind of see that here, right? There's missing points of the low moment data as we go through here. And even within the low moment data, some stations, which is represented as a vertical slice along this line, have missing data points. And when I replaced all of those with NANs earlier, Matplotlib is smart enough to just not plot the data if it's a NAN. That's basically why I did that, so we can see it very easily here. Also plot the high moment data on top of that. And, give it a label. Good practice. Could probably label the vertical component if I wanted as well, but. So here, this is all of the low moment and high moment data. So you should notice here that they're already on the same scale. So this low moment and high moment data have been processed. Part of that processing is normalizing the data for this transmitter area, the number of turns in the loop, the current in the loop as well. So these data are on the same scale. So essentially this would be produced by a almost produced by a magnetic dipole with a unit magnetic dipole moment. We can see we at least have low moment data at every sign. But now let's select a single sounding along that line. Already gone through this, and record 5590 is pretty good. So let's grab that station. I could group by the record again if I wanted to, because it's also like that line is itself a pandas data frame. But I can also just grab it where the line, that record index, is equal to the station I want to look at. So this is going to return a data frame here that only has a single station in it. And then similarly to what I did before is I'm going to grab those associated with that. So let's split this cell so you can see what the station looks like on its own. Right, so it's just essentially one long line of data. So I then just, if I want to work with this data, I want to grab these bits of information from it. So all the low moment data, all the standard deviations of the low moment data. So right, so we've got 9 plus the number of low moment gates, and then I start from there, go 2 times the low moment gates, and so on. You'll also notice that right here, I'm taking the chance to convert all of these things to numpy arrays. SimPEG is going to want all of this sort of information to be in numpy arrays. So I'm going to do it now, so I don't have to worry about it later. I've grabbed all the data set there. And let's add some information, because I want you guys to see where this is at, right? Where this station that we chose is at. So this is going to plot all of the data, all of the locations of the data of every station, right? Let's plot the location of those lines. So line ETMX. Automatically going to plot us with a different color. And let's put that station that we chose on there as well. Let's make it bigger and give it a star. So our station is right along here. The line that we're focused in is on this orange line. And we're going to invert for some data right here. Along that line, so this is, I'll show you where the data, that station is along the line of data that we plotted by just adding a simple V line across the plot. The station, right, we're plotting against Y, so I have to specifically get this thing for this function to work, but you should see. So this is where our station is at along the line. So this is the inversion we're going to run here, and we're going to model this data set. So there's a few more things that we need to know in order to model this. So we've gone through, we've selected the data set or the station that we're going to be working with, gotten the data values themselves associated with these split up into a low moment and high moment pairs. And then we will have to get a few other things in here. So the first thing, in order to model this data set, we need to know the location in time of all of these measurements. So that came from that time gate information from the configuration file. And we will need to know the waveforms of the transmitters to model them. These have not been deconvolved or anything to form some sort of step response. They're just the recorded data processed, averaged, and so on, and normalized. So we'll need to know the waveforms for each of the low moment and high moment to be able to accurately model them. We will be able to represent the shape of that transmitter, that hexagonal shape, and also model the location of the receiver relative to that. So inside the GEX file, there's a few bits of information. So here is all of the gate centers. So this bit of information corresponds to all of these gate times here. So there's all of these gate times. What I remember, it's the center of the gates, the start of the gates, and the end of the gate. So a time gate is this sort of window of information where the machine integrates and then averages the data set that's coming in. So I'm grabbing all the time gates in the center. Now these are the like the base times of this data that's recorded. Each channel has options where you can sort of shift these and scale them around and move them. But in general, the time for each of these channels is going to look something like the gate centers plus a shift plus some sort of delay. And then we also, you'll notice from that file up here, right, that there are the number of time gates goes from 1 to 37. Well, we didn't have 37 data sets in all of them either. Remember the configuration file told us which initial gates to remove and the total number of gates. So we're going to have to take that into account first as well. So it'll essentially go from the first gate, which is the remove initial gates, to the last gate. Or our low moment times, right, are going to be all of the gate centers from the first gate to the last gate, plus whatever our shift was. So the shift was this channel, came from channel 1, that was the low moment information, right? So there's the shift and there's a delay. Correspondingly, I've named all of these very conveniently to be those same values down here, so I can just, for the high moment times, same thing, right? Gate centers, this will be the first gate of the high moment, last gate of the high moment, the shift and delay of each of those. Now that finally gives us the times when our data is recorded. At this point, I'm going to take a quick step to actually just discard all of those NANDs that are in this station. When we do an inversion, we don't want there to be NANDs in our data set because things tend to blow up around them and it doesn't know what to do with how to minimize it. So let's just discard them all, move on. So I've removed all of those points at this station that have NANDs at them. So we're only left for this station those points. Now let's plot our data set. Let's see what this time decay curve looks like. So on a log scale here, so log in time. Let's plot that low moment data set, right? Yeah, pretty nice decay curve there. It goes around on through. So this is the low moment data. The high moment data on top of that, since they've already been normalized. You see, obviously, that they don't perfectly line up with each other through here, and that's mostly due to the difference in waveforms at that time. The waveforms are not the same between the two. But we can see our characteristic decay curves. So this is the decay of the B field over time, the rate of decay of the B field. And this is the data that we want to kind of play with. We want to invert this data. We want to try to match, find a model that recreates this data set. Okay, so there's a few more. Now we have all the data set. We know when it was taken. We have the times associated with it. We want to represent sort of all of this structure of the SkyTime system with SimPEG, because we haven't actually used anything with SimPEG yet. We've all just been reading in data. We used a bit of pandas, NumPy, Matplotlib. We want to represent all of this with SimPEG. Now, the general structure of how we hold this information in SimPEG is through a combination of receiver objects, source objects, and survey. We combine all of the sources and receivers into a survey. You think of them exactly as their physical representation, right? A receiver observes the data. Sources create fields that the receivers listen to, and then the survey is all of the sources put together. and all of the receivers. Specifically in the time domain EM module, our receivers have a location associated with them, or multiple locations. They have locations associated with them. They observe some sort of specific component of data. So here is the vertical component of dBdt at specific times. So those time date centers that we've already calculated. The sources have specific types. So there can be a line current source, there could be a magnetic dipole source, a few other ones. They have a location or a set of locations if you're defining line currents. So they have to have starts, ends, or if you're making a loop. A source has a waveform associated with it, and it is listened to by receivers. So we have to have all of these things and attach them to source. So all of this information that we need is going to be in that configuration file that we've already processed. So let's start by grabbing that waveform information. So the waveform depends on the low moment, and excuse me, there are has been discretized in time. So this waveform has been discretized in time, and I'll show that once I get it. So I'm going to grab this information about the waveforms. I've got the waves. I'm going to grab the low moment wave, ask for its time. Same thing, I'm going to ask for, so this is the points where it has been discretized in time, and this is the shape of the wave, or its wave, the form of the wave. Be able to do something very similar again for this high moment, right? High moment. I've got these, and let's plot them and see what it looks like. I'm just plotting waveform in time of both of the high moment and low moments. So see, this is the low moment on the left and the high moment on the right. They're normalized to have a maximum of 1, which will work with our data set because it has been normalized for a source current of 1. But they're not the same, right? The high moment is this sort of like triangular-ish curve. So low moment is a triangular curve. The high moment has this sort of almost half sine, quarter sine ramp off, and then a very quick ramp off. This is what these waveforms look like. They're not the same. We have to take care of that. We then need to know the shapes of these receivers and the shapes of the transmitter. So that was also in that configuration file. So this, right, the general section, and we had TX boost points. Right, so this is all of those points on the array. Plot them. These are all those points, right? And as you saw, this was the points of that array. The question is, think about, is it going to go clockwise or counterclockwise here? So it starts at -12, -2.5, goes to -6, 8.5, -8, going on. So these points are listed counterclockwise, right? So if we take our right-hand rule, that means that the positive direction of this is going to be directly out of your screen, right? In SimP, we'll think about that as we're plotting our data. But right now, the positive direction is out of our screen, which is, in this case, will be directly vertical. So that the positive pathway of this is going to be directly up. So the B field is going to be going up in the center. In SimPEG, we're going to have to do a few other things, points to this, but I'll deal with that later. We also have our receiver offset. So this is the location of the receiver relative to that point. So it's in this RX offset has 3 components because the receiver itself is actually a little bit offset from the loop vertically. You can see it pops up right over here. So this is where the receiver is, and we have this hexagonal loop. So we have those values. Let's get them into SimPEG. Our shape, our offset. One of the first things I'm going to need to do is actually expand this to be a 3D thing. So this thing lives in 3D space, right? So I'm going to use NumPy to expand this thing out, to give it another column. This command will also add another row at the very bottom of this as well, which is going to be useful because in SimPEG, to write this, so far I just added another column and another row. In SimPEG, to represent this loop, it's a closed loop. So that means we have to close the loop ourselves. We have to add a point at the very end that's going to close that loop. And that is just the first point. Right? So I'm going to set that. So now our loop is closed. It completes all the way around. I know what's happening. I did that a couple times already, right? So padding it and doing this. I only want to do this work once because I'm going to keep overwriting the same array. Put this cell here. Right, so our loop is closed. The last point is the same as the first point. We have to orient these things in 3D space. So I'm going to find the location. I'm going to add on. Let's add on the location of the station. So that little iLock there, that little command at the end is just grabbing the actual value of that point. Well, otherwise, it's just going to return a pandas data frame object, and I need to get a specific value from there to make it work. So I've got so on Y location and its altitude. Here I'm going to use this inverted altitude. In the processing step, there's a step that inverts for the altitude of the loop above the surface. That works well with a 1D model, so I'm just going to use that from this. You could also use the altitude itself, but they both work. So I'm also going to add that absolute value, that station position to the location, and also I need that. I'm going to need that transmitter area. So if I'm going to represent this loop in SimPEG, it's going to actually represent that loop. It's going to generate the area or the data that loop would create. So that loop is, has an area associated with it. So we actually have to undo. We'll have to undo that area normalization to match this data that we're going to generate with SimPEG. So let's grab that area, transmitter area. Okay, so we have all those pieces, everything we need. Finally, we can make the SimPEG stuff. There's a lot of stuff in here, right? So we often asked how we represent the SkyTemp system using SimPEG, how we represent both those high moment and low moment data sets. If we think about the structure really quick, we can have multiple sources in a survey. We can have multiple sources. So what we do is we break up the data, like as we've done already. We break up these sources, even though they're in the same location, they have two different waveforms, and we have to model them as separate sources. So as starting with this, we start with our receiver, right? It has a location. It has times associated with when they happen. And we said it has a specific orientation. Right? It's observing the Z component of the magnetic flux time derivative, and it's observing it at a point. Our waveform let's get that waveform into SimPEG. All of the receivers of the time domain live in this receiver subpackage here. All the sources and waveforms live in the sources subpackage. So we have this piecewise linear waveform, which is already, we'll assume, a linear between 2 points. Let's give it all the times. And the shape of it. Now our source is a line current source, and it's a path, right? It's that hexagonal path. So it has, first of all, it listens. It has a receiver that listens to it. It has a location. And this transmitter location is the location of all those points. And it has a waveform associated with it. Oh, we have our source object. Turns out well nicely at the moment, but general process is, right, we set up a receiver. We create a source that has a waveform and a certain line current, a property. We attach the receiver to it, and then the receiver will be able to listen to it. Be able to do all this same stuff, right, just with the high moment data sets. So they've been split up in between. So now it's at the high moment times. Our waveform at the high moment shape, maybe high moment. And our source just those things as well. There we go. We have two sources here that each have a single receiver object attached to them. We combine these together in a survey. We're going to pass a list of sources to it. So the low moment and the high moment. Now this represents the survey parameters, all the acquisition stuff that we've gone through. And now let's create our simulation. We actually want to do some forward modeling with this, right? So we're going to use this 1D layered simulation to create thicknesses and conductivity. So there's some properties, this layered simulation. We're going to use a 1D thing for this tutorial because it's rather quick to run and quick to get through. We have thicknesses and conductivities. It has these properties with it. Right now, this has just a single conductivity, so it's literally just a half space. We're going to use that simulation to predict some data. So that's this dpred function. I'm passing it this none here because I don't have a model. I'll talk about that in a little bit. We predict the data. I'm going to get the low moment and high moment data sets and plot them. So I have to add a negative here because of SimPEG's convention. So in SimPEG, Z is positive up. And this data set, Z is positive down. So run it, runs pretty quick. Here we go. I can directly assign to these if I want to change the conductivity, right? 2, 1. You can see how it goes. And it's starting to iterate. We can do it this way very simply and adjust them. Let's say I want to have multiple layers. So I'm going to have one layer that has 10 meters. And our conductivity model has to be the number of thicknesses plus 1 because the last layer is assumed to be infinite thickness. 2 layers here. And keep going. So this is how you basically can work with this simulation object to predict data. It has properties that we assign to. I know that was a lot. There's a lot of steps to get this survey set up and running. But now that we have this simulation, we can do a lot of fun things with it. We know how to set this up. That brings us to the inversion. Now there's a lot of pieces that I will go through. There are maps, data objects, objective functions, minimization routines, directives, inversions. All of these pieces are here. We'll go through them all. But let's start with a map. So a map is a sort of very simple thing. In SimPEG, it does this sort of transformation. So for example, there's a simple map that takes an exponential transform of the input. Exponential map. All right, it's going to take this, it's going to, for example, right, if I can multiply things by that map, so it's going to be e to the -5, so 0.06. So I have this map and it essentially it transforms the input by multiplication. In SimPEG, it's going to be particularly useful for two reasons. Generally, conductivities are on some sort of logarithmic scale. So we can represent that using this logarithmic exponential transform. And we also need to ensure that the conductivities are positive. So this is going to allow us to not have to put any sort of positivity constraint on a model. So maps are used in SimPEG to say how we go from a model to our physical property. We're going to need these maps. We're also going to need to encapsulate our data in this sort of data object that says it knows its data, it knows its standard deviations, its errors. It also knows its survey. So here I'm multiplying by the transmitter area of the station, the low moment data set, and I need to negate it because of the conventions are different between SimPEG and the SkyTemp survey. So I'm making it consistent with SimPEG. The relative errors are in the same order. I can combine these all of these into this data container. Right, so this container needs to know the information about the survey, the observed data set, and we can also tell it that we're going to be passing it a relative error. What's neat about this data container is that we can actually index it with sources and receivers. So if I wanted to know the data that was associated with a particular source and receiver pair, I can pass them directly to this data container, and it'll tell me the data that was associated with it. It's also useful to make sure that we've passed the data in the right order, that we've attached the right thing to the right parts. Okay, so we introduce maps, we've got a container for our data. I'm going to create the next thing we're going to do is a parametric half space inversion. So I'm going to solve for that simple half space. I'm going to use it to explain a few different key components, but let's set up a new simulation that we're going to use. So in order to tell SimPEG that we're going to invert for something, we pass it that the physical property is going to be determined by a map. So here, the conductivity is going to be determined by an exponential map related to a model. What I mean by that is that if we define our model, right? So I'm assigning the model value to be this sort of log of 1e to the -5. The simulation knows how to take that and transform it to a conductivity, right? So the value is log 1e to the -5, and it knows that conductivity is 1e to the -5. This is what we use to tell SimPEG what we're inverting for. So right now we're just going to invert for a conductivity. Go on. What we do, SimPEG treats inversion as a minimization. Lindsay brought this up before. We have in order to minimize it, we need to have an objective function. This is in general our objective function for regularized inversion. But right now we're just starting with a parametric inversion. And all we need to do that is define a data misfit. We don't need to regularize anything just yet. So our data misfit function will need to know how to compute data. So it's probably going to take the simulation, because that's how data is computed. And then it's going to compare it to the data that we've observed. So it's going to take that data container object. Go through here. I'm going to define this objective function. It's going to be an L2 data misfit, right? We pass it our container in the simulation that's going to forward model, right? This function evaluates. Let's say we have a model It's the log of 1 e to the minus 2. We can evaluate this function. That's this data misfit function for this model, right? I could do this very coarsely minimization by hand and just sort of make this thing as small as I possibly could, right? But let's do that automated. That's going to take a while. Let's go back to here. Where did I start at? E to minus 2. Yeah, go there. So we need to optimize this function. We need to find the minimum value of our model that makes this, or the value of our model that minimizes this function. Do that through optimization. Going to grab a specific minimization routine that has some properties to it. This is an inexact Gauss-Newton. We're using Gauss-Newton because this is a traditional one that you use for nonlinear least squares inversions, right? Gauss-Newton. And it's inexact because we're using conjugate gradient to solve for that step direction. We have this minimizer. And then we need to set up the problem that we're going to minimize completely. An odd quirk about SimPEG is that we can never not have a regularization at the moment. But what we can do is just make one that that has the same number of parameters as our model. So it has one parameter here, and then set beta to 0 and ignore it, right? So let's set up this inverse problem here. So this inverse problem represents the sum of this phi d plus phi m. Like I said, we're going to set beta to 0 because we want to ignore phi m at the moment. So it has the function, right? Our phi d plus our regularization, but it's multiplied by 0. And then we attach a minimization routine to that function. So this inverse problem is that objective function and then how we're going to minimize that objective function. Okay. Get our inversion going. So there's a separate distinction between the inversion problem and the actual inversion. The inversion problem is that function that we want to minimize and how we minimize it. The inversion is sort of a broader concept thing. It takes that problem and actually runs the problem. So we set up our inversion, we pass it our problem, and we run it. We have to give it some sort of initial model. Right? So it's going to sit here, it's going to run, going to go through a few iterations until it converges. So you see the phi d measure. This phi m, it splits it out, but it doesn't really mean anything, right? Because we're multiplying by beta 0. You'll see that the function evaluation is actually the same as the data misfit. And then we see that the difference is decreasing over iteration from one step to the next. And we get a final model out of it, a recovered model. So, well, what was that best fitting half space? Let's just make use of the map that's already on that inversion object. And we see that the conductivity was 0.2, pretty high, right? Generally pretty high. Well, as we talked about, Lindsay brought up, this is a saltwater intrusion problem, so we might expect conductivities to be a little higher than we might see other places. So not off, not too far back. Let's look at the data. I'm going to introduce you guys to another new function here. This is called a make synthetic data. Instead of returning an array as dpred did, this is actually just going to return a data container object that we can use. So this is a data container object. And let's plot this data. So I'm going to be plotting data a couple times and comparing it. So I've defined this as a function, right? We're plotting the low moment, high moment data. See how I'm indexing it with those sources and receivers there. It's pretty slick. And plot it. So this is how well the 1D model fits that data set. Not too bad, but we could probably do better. And it's at least a good place to start. Okay, let's move up a little bit. Let's have multiple layers here instead of just one. So to do that, you make use of this thing called a wire map. And now our model here is going to be 2 conductivity values and a thickness. So if that is our model vector, we need to tell SimPEG how to go from those 3 values, separate them into a conductivity and a thickness, and also take care of some maps in, right? So this wire map already takes care of that, right? So I'm going to have 2 conductivity values and 1 thickness value. creates these nice little maps for us. So wire map sigma, wire map thicknesses, those are keyed by the names of these parameters. And then I'm going to attach an exponential map at the end of it. So our models are still going to be exponential values of conductivity and thicknesses. Set up an initial model here. Let's use that best fitting half space as our initial model, because it's actually a pretty good place to start. So I'm getting the value of our recovered model, which is already in log space, assigning it to our initial sigma model. Let's say that we have one value, and it's the log of 10. So I'm creating an array that is one length, has a value of 10 here. Here I'm creating a layer that has a length 2, and it has the same value in both of them. And our simulation now needs a map for both conductivity and thicknesses. This will tell us how to go from our model to conductivity and thicknesses, right? So if we assign our model, our initial model here, to the simulation inversion, right, we should be able to see that it correctly got those sigma values. Conductivity, yep, as a half space conductivity. This thicknesses should come back as 10. Even though our model was the log of those values, right? Okay, so same process, set up our data misfit, set up a minimization function for that, make our empty regularization, but now it has to have 3 parameters to it, and set up our inversion problem. Again, I'm just setting beta to 0 and ignoring it. Let's run it, shall we? Might take a little bit longer because now there's 3 things to invert for, not 1, but not too much, because the initial model is actually a pretty good starting point. Again, I'm going to make that synthetic data. And then let's also look at what the recovered values for these things were. So we had a layer 0.1, layer 0.2 conductivity, and it was about 6 meters thick. See what that looks like. So this vertical line here was the half space, that best fitting half space. And this is our recovered 2-layer model. Now you could go back and redo all these things with like 3 layers and 4 layers and so on to find initial data set. But what you can also see here is that our final data misfit here was definitely lower than our data misfit for the half space. So it fits our data better. It should look a little closer, right? So we're going to go here. Let's plot this predicted data. Definitely looks closer. Not too bad. So we keep going this route, keep adding more and more data sets, more and more layers. At some point, we start entering the realm of what is regularized inversion. So I was ignoring that regularization term before, so now let's look at it a little bit closer here. First of all, we're going to need to set up a mesh. We need to define something to regularize a space where our model lives. Also, what we're going to do is we're going to set the thicknesses specifically. So now we're only going to invert for conductivity, but we're going to invert for conductivity at many locations. And those locations are defined by this mesh. Right, so we have this mesh here. What I'm going to do is I'm going to create an array that starts with a cell width of 1, and afterwards expands out for another 63 parameters by a factor of 1.5 each time. Right, so it follows this sort of shorthand. This is SimPEG will expand this out automatically, or discretize actually will. So we'll create our mesh. Maybe we have this tensor mesh, just 1 dimension. And you can see it has a cell width start at 1.0, they end at 21.6. It has this sort of mesh extent of 434 meters as we're going up. So one of the things that you'll see is that this mesh in SimPEG, let's set up our simulation object that corresponds to this example here. So we have our simulation 1D, attach our same survey. Our conductivity map is an exponential mapping again, but now we have to tell it the thicknesses. So this is giving the thicknesses of each layer. The The values of all these, so there's 63 values of 64 values of this. And they're going to, simulation 1D layer is going to assume that they start from the top and work down. So we're starting with small, getting bigger as we go on. I'm also going to ignore this last one here because our conductivity values should be one larger than this. So we're going to look for 64 conductivity values. And this thing was 64 length, so we have to cut one off. And set up our data misfit through. And now we need to set up our regularization, so that phi m portion. What I'm going to use is I'm going to measure this sort of, actually, it's as I'm looking at this. So we're going to measure the model, the size of the model, and its spatial derivative. There's some squareds in there as well, but essentially what we're doing. We're measuring the size of the model and the data misfit. There is a regularization term in here. The regularization module, SimPEG, has this weighted least squares. So this thing is going to set up this function for us. It's also going to give us some decent starting parameters for this alpha, these weighting parameters out front of each of these terms. So we have our regularization object. Let's find our initial model again. I'm just using that half space as a starting model. Got our regularization going. This is our initial model for the regularization problem that we're going to solve. Got our minimizer again. Set up our inversion problem. I'm going to set up this inversion problem now. So here, our inversion problem, right? Before we had beta is equal to 0. What I'm going to do is the same base inversion problem, our regularization objective function. Now I get to pass this actual full-fledged regularization to this problem. And let's start with a beta of something, maybe 10, sure. And we get to run our inversion. It might take a little bit longer because now there's about 64 of them going, 64 of those unknowns. And I'll wait for that to go on. It shouldn't be more than a couple of seconds here. But as you can see, it's iterating through, it's decreasing the data misfit and increasing this phi m, but the total objective function is decreasing in time. At some point, it'll either hit our maximum number of iterations or it'll reach a minimum in the function. So that's what it's done. Finished the minimum here. Plot our model. So I'm going to create the data from that regularization object or from that recovered model. I'm going to plot the recovered values from our 2-layer model, our single layer model, and now our continuous approximation to that. Okay, so we can already see it's like it's wanting to do a little bit more. And the data misfit is actually already lower than that 2-layer model. See here. We're wanting to fit this. Now I could go and adjust this parameter every time. So if I decrease beta, it'll likely fit the data a little bit better. But it's going to be kind of cumbersome to keep running these over and over to find a value that you want. And it's kind of arbitrary. It's also depending on that noise level that we gave it at the beginning, this data misfit term, but it'll keep going. Let's sort of automate that process, right? So this keeps running. You'll see that with a lower data misfit, this model is going to look a little bit more chaotic. And it's a little bit more bump, a little bit wavier, a few more changes in it. We can already see some sort of parameters, some characteristics forming in this model here. Our data certainly fits a little bit better than before even. The near surface is a little bit off, but if we are new on noise level, we could simply keep looking for a data a beta that fit our data misfit term to this sort of ND over 2, our expected number, or number of data divided by 2. If we got to there, we'd say it's a good model, or go on. But you can actually have SimPEG sort of automate that process. We use those through this thing called directives. So directives change parameters of the inversion as they go on. So very simply, I have a directive that's going to cool the beta over time. So it's going to decrease beta by a factor of 5 every 2 iterations of that minimization function. I'm also going to add a directive that's going to allow me to retrieve the values of both the model and those objective functions in time. So I have 2 directives, one that's going to decrease beta and one that's going to save the values of it. I start up my minimization. This time I'm going to let it run a little bit longer here, actually. I'm going to do a few more iterations. Let's start at a higher beta value here, just to get a good curve here. So 10,000. Yeah, that seems reasonable. Okay. Same thing, right? Have our initial model again, going through. And now you'll see that beta is going to start at that 10,000, and then it's going to decrease every 2 iterations. So this directive is controlling this beta parameter for me. Right? So it's going to take a little bit of time to run, keep going forward. Going on. And then all of these values are going to be saved in that directive that we created, that save dictionary directive. Inside of it, there is it knows about the optimization function, the number of iterations, and there's also this outdict, this dictionary of the outputs of every one of these, and it's keyed by that iteration number. And the iteration number is going to range from 1 to the number of iterations. 1, 2, 3, 4, 5, 6, 7, 8, and so on. I believe this actually goes from 1 to that plus 1. Let me check real quick. So it's still running. See it decreasing beta every time. Data misfit getting smaller. Model objective function getting larger as it goes on. That's what we would expect. I've just grabbed all of these values. So our phi d, phi m, and the beta value at each iteration. Yeah. So there's actually it saves them from 1 to the number of iterations. So I've added +1 here to make that work. Okay. Let's look at these plots really quick. I'm going to make a, you might have seen this sort of thing as like an L curve almost. What I'm going to do, I'm going to log plot. Let's look at ID versus the betas. Right, this should decrease as betas increase. Right, so small data misfit. Large data misfit. Model objective function should go the other way. It decreases as beta increases. And then let's look at something called the L curve, which is generally the data misfit versus the model norm, or the model objective. So it's a little jittery, but that's kind of because we're not explicitly solving these equations at each beta, explicitly memorizing it. But what we're looking for is this kind of trade-off between where the data misfit is decreasing rapidly, and then the model norm starts increasing rapidly relative to that. It's characteristic by this sort of corner here. So we might say that we've got some data points down here. Let's look at that. I believe it's around this 14th one. Yeah, it's reasonable spot, maybe 15. Check it out. Yeah, that's a decent point for an L curve. We could be a lot more rigorous about this and compute some curvatures of this and compute some maximums. But in the meantime, we can just kind of look at it for now. Okay, so now what does the model and the data look like at this point? So again, compute some data, thicknesses, plot our model. So the regularization compared to that. So I'm gonna copy this cell very quickly here. Plot in that same order. So this was at a regularization parameter of 5. And after our 15th inversion, the regularization parameter is 0.1 about. So we expect this model to have a little bit larger variation in it, right? So our final model is going to be stored in that saved dictionary. And the outdix is going to be the 15th one, we said. And it's the N, the model. There we go. So this is the model according to that sort of L curve criterion, that sort of spot there. And we do that L curve if we don't have a good estimate of our data, or at least a good, reason to suspect that this standard deviations or those errors are good. But we can also use it to verify those errors. So definitely has a lot more chaotic properties to it, right? But there's still some smoothness to it, some layers that we can start to pick out in here. Look at the data fit. It's pretty good, right? It's picking up all those. It fits the near surface better than before. With late times, pretty good. We're catching all those little dips in our times there. And it looks pretty good overall. So you might then ask, well, what is like the error that was associated with this data at this model? So we have our data level. We can compute a relative difference between the predicted and the observed data. So this is the observed data. That predicted data, their difference divided by the observed data. And so this is a relative difference between the predicted and the observed. And this will give us some sort of estimate at each point of that sort of standard deviation. But overall, let's look at the mean of this whole thing to get a sort of average standard deviation. So we're saying that on average, the relative difference was about 0.35 or 3.5%, which is actually, right, from our data container, not too far off from what was assumed in our data relative errors. So I would have a reason to suspect that these are a good estimate of the data. Hopefully that introduced all of you guys to a lot of the concepts in SimPEG. I obviously didn't hear Lindsay interrupt me with any Q&As or anything, so assuming everybody got through it or was able to walk through it. They're the decay curves are the decay of the B field, right? So the rate of change of the B field.
Thanks, Joe. I'll jump with.
Yeah. Oh, sorry. I was responding to a question I already saw on there. So yeah, someone asked if those decay curves were. I might have offhandedly referred to them as B field, but I think I said that they were the decay of the B field, right? So that's why I said that they are the dB/dt curves.
Awesome. Thanks, Joe. I just wanted to jump in perhaps with one more comment at the end as you get a final inversion result. And in general, it's also a good idea to look at models earlier on. I mean, when you see this much structure in a model and you see, those noise values, sometimes the noise values that are provided from the processing are a bit lower perhaps than what you would expect or what the true noise levels are. And so in general, it's a really good idea to look at a few different models and kind of gauge and ask questions of, do you actually believe that there is that much structure in the recovered model? Because when you see that much, that it's easy for somebody to interpret that geologically, and you want to make sure that that's something robust and that you trust. Yeah. So something like this, if you go back earlier in the iterations when beta is larger, you're going to get back something that's more influenced by regularization.
Right. So so I can show that right here, right? So we're looking at these dates here. So there's a larger beta, smoother as we go on. Later iterations, you can see those layers there really do want to, like the data does want to pull those layers out into this inversion, right? So
Awesome.
A few questions. So this is essentially it's a layered inversion. There are tools for doing structurally constrained inversions in SimPEG at the moment. And it was definitely beyond the kind of scope of what I wanted to show here, had time to show here. But it was definitely there. Like there's pieces to it, and I will probably actually add some another tutorials if you want to keep an eye on this GitHub repository, though, demonstrating how you can do those sort of structurally constrained inversions, longer line, or even the laterally constrained inversions as well. But they're all 1D layered inversions. The low pass filter. Someone else asked about the low pass filter on SkyTem. At the moment, we don't have the capability of handling that with SkyTem or with the SimPEG, but there will be ways to bring it in. I think Sagi might have a few comments on that low pass filter because I know he's thought about it a couple times. Any thoughts, Sagi?
Like the current SimPEG branch doesn't take into account, but we have a few local developed branches which takes into account, and it does include like SCI, LCI types of inversion as well. But the point here is we're trying to provide more fundamental 1D tool. Once you have the 1D tool, it's more stitching things together. So and there are actually quite a few other details which I think are not quite open. So we're happy to implement as long as there's a clear description about all the parameters and how that's implemented. But we did our best so far. So typically when I'm inverting SkyTem data, I test with the Aarhus Workbench code and see the predicted data from SimPEG code actually matches okay for a given resistivity. So that's the kind of current form of the process, but I think we could implement later.
I think there was a code about identifying and removing coupling or data contamination. I have a feeling, Sagi, you probably have thoughts on those as well.
Well, so actually Tad Ash is here, so who actually did the processing. So Tad can actually better answer those questions. But I think as far as I understand, we basically used the Aarhus Workbench code. Tad actually used and then there are some automatic part, but mostly manual sort of like removal of noise was done, like power line effect and stuff like that. Yeah, in our local branch, we have a bit of functions that you could actually visualize the stitched 1D code, but not in our main SimPEG branch. So later, maybe Joe, as Joe said, we could provide like, a couple other tutorials.
Yeah, somebody had asked where the data location of that founding was. So we were along this line, and it's this star right here, this point right in the sort of the middle of it. The coastline follows along this area at about 5 kilometers or so from the coastline, roughly. And then along that line, it exists here.
Excellent. Awesome. Yeah. Thank you all so much for such great and thorough presentation. It's great to really just like walk through all the steps of this workflow of importing, processing, and inverting some SkyTem data. Like that was really cool to kind of see that whole thing come into pass.
Yeah, there's a lot of pieces to represent, a lot of things to get in there. So one of the things I want to emphasize really quickly though is that setting up this survey to get all this parameters in here, I could have, like, that was independent of that simulation we used, right? If I really wanted to, I could have gone and used a 3D simulation, a full 3D dependent simulation, and attached that same survey object to it. So all those things would be, the setups are all similar. They all have sort of physical properties associated with them. When you get to 3D, you have to start dealing with like mesh discretization errors and things, but yeah. see, Alejandro asked about the 2D MT. There is a forward operator available in SimPEG for it at the moment. We don't have many tutorials with it, but it is there. It's in the release version.
Excellent. Awesome. So I think pretty much at time there, unless anyone has any last minute additional questions. Going once, going twice. Excellent. All right. Well, thank you everyone on the SimPEG team. Thank you, Joseph. Thank you, Lindsay. Thank you, Soggy, for joining us and taking the time to step through all this with us. For anyone, thank you everyone who took the time to come to today's webinar. Very active in asking questions and going through the tutorial with Joseph there. Like I had mentioned a couple times, the recording of this webinar will be available on the SEG YouTube page in the open source software playlist. Usually takes about a week or so, depending on how quickly we're able to get to it when it comes to like editing the recording, but it'll be thrown up there within enough time. I know we will also be having another open source webinar some point in March, I believe, and talking to some of the folks from the PyGimli team. But yeah, if anyone has any further questions, I mean, I know as with any of the open source softwares, like I'm sure people can submit issues or questions on the GitHub page, or recommendations for other stuff that they like to see or questions about additional tutorials or whatnot.
Feel free to reach out to us on Slack as well. It's probably the quickest way to get a hold of any of us.
There. Yeah. Excellent. So thank you all again for coming to the SEG Near Surface Technical Section Student Subcommittee's webinar on open source software featuring SimPEG. Thank you again to Joseph, Lindsay, and Soggy for taking the time today. And yeah, everyone have a wonderful day, and I'm sure we'll hopefully see you again soon.
Thanks for having us.